In this video, we're going to cover what are called the sum and difference identities. These are identities involving the trig function, sine, cosine, tangent, and so on, where inside of the function, you are either adding two angles or subtracting two angles. And you see we have identities here for sine, cosine, and tangent. And if you wanted any of the other three, secant, cosecant, cotangent, you would just use the reciprocal identities in order to get those answers. Now, I'm not going to prove these six identities are true in this video or ever. It's kind of a gigantic mess to prove these. You have to draw the unit circle, draw the angle A, angle B, and use a bunch of geometry to get the answer. If you'd like to find those, I'm sure you can find it in other videos or in your textbook. It's a mess, but we're going to take these as just given for this class. We are going to be able to use these to prove other useful identities. But let me just go over them quickly here. The first one says sine of two angles added is going to give the same answer as if you do sine of the first angle, cosine of the second angle, plus sine of the second angle times cosine of the first. So it's kind of like you get sine and cosine of each of the angles in different combinations, and that's how you get sine of A plus B. Sine of A minus B is almost the exact same result, except the minus on the inside gets carried into the formula here to be minus on the right side. Similarly, cosine A plus B and cosine A minus B are going to be almost the same identity. It's not this time though. Instead of it being sine cosine, it goes cosine of the first angle, cosine of the second angle, and then sine of the first angle, sine of the second angle. So you got cosine, and then sine. Another difference this time is that if it's a plus inside, it's actually going to be a minus on the right side, and if it's a minus on the inside, it's going to be a plus on the right side here. So you got to remember the cosine just flips the sign of what you're doing to the angles, whereas the sine keeps it the same. I do want to say that I don't expect my students to memorize these identities here. These are ones that I would give on a formula sheet on an exam. They're very useful identities, but they're kind of difficult to remember for most people, and I don't consider them as fundamental as like the Pythagorean identities, where like those I expect all my students just to know off the top of their head. These ones are something that I feel like you can look up if you really need to know it. Maybe even worse are the tangent ones here. I'll go ahead and give them there, but we don't really use them that often. But if you have tangent of a sum of two angles, you get this fraction, tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first times tangent of the second. And then you get to play around with your minus signs and plus signs on the A minus B identity there. So you might say, well, why do we care about these identities? Well, let's take a look at this first problem here. It says, find the exact value of sine of 75 degrees. Before these identities, we had no way to solve this problem. We know angles that are like 30, 60, 90 right triangles. We know 45, 45, 90 right triangles. There is no special triangle with 75 degrees. It's not there. And we could use a calculator to get the answer, but that's only going to be an approximate answer because you're rounding decimals, right? If you want an exact answer, you need to use some other method. And it turns out it's going to be really straightforward once we have these identities. So sine of 75 degrees is the same as sine of 30 degrees plus 45 degrees, because 30 plus 45 is 75. Now I can use my first identity up here. It's going to go sine of the first angle, cosine of the second angle, plus sine of the second angle, cosine of the first angle. And then we use our special values of sine and cosine. Sine of 30 is 1/2. Cosine of 45 is 1 over root 2. Sine of 45 is also 1 over root 2. And cosine of 30 is square root 3 over 2. And so there's going to be 1 over 2 root 2 plus the square root 3 over 2 root 2. And if we want to combine that together, I'll rewrite it a little bit. Square root 3 plus 1 over 2 root 2. And so this right here, expression with square roots, this is the exact value of sine of 75 degrees. So using these new sum and difference identities, we can get the exact value of sine, cosine, tangent of other angles that were not able to be done before now. Again, before now, if you memorize those points in the unit circle, those points always either came from the 30, 60, 90 right triangle or the 45, 45, 90 right triangle, nothing else. This allows us to go beyond those and get other angles by adding or subtracting them. Instead of doing 30 degrees plus 45, I could have done 45 minus 30, and I could find the sine, cosine, tangent of 15 degrees. So these are all things you can do now that you have these sum and difference identities. You can also prove new identities like this one down here that says cosine of 90 degrees minus x is equal to sine of x. Well, we start on the more complicated side. Cosine of 90 minus x using the cosine A minus B identity would be cosine of the first thing, cosine 90, cosine of the second thing, x, plus sine of the first thing, sine 90, sine of the second thing, sine x. And then we know cosine of 90 is 0. So multiplied by cosine x is going to go away. We know sine of 90 is 1. So it's going to be 0 plus 1 times sine x, which gives us the answer sine x that we're looking for. We've proved this identity. And in fact, I want to mention why I chose this identity here. It's not just some random thing. If you think about 90 minus x, if I draw myself a right triangle here, if I have one angle, the other angle is going to be 90 minus x. It's the complementary angle. And what this identity shows you is that if you're using the complementary angle and the complementary function, cosine, it's the same as if you didn't use either one of those complementaries. So sine of an angle is the same as cosine of the complement of the angle. And in fact, that's where the whole co in cosine comes from. It comes from complement. So sine of any angle is cosine of the complement of the angle. Secant of any angle is cosecant of the complement of the angle. Tangent of an angle is cotangent of the complement of the angle. So that's where the co comes from. Cosine is complementary sine. Cosecant is complementary secant, and so on. And only now, today, can we actually see where that idea comes from, why they're called that way, because now we have the sum and difference identity. So these are very powerful identities, and yet still something I don't really think you need to memorize, more just understand how to apply them.